past decade, additive manufacturing has exploded to the point that it's now considered a disruptive technology. It has fundamentally revised how we view manufacturing across a wide variety of industries. In addition, it is now so widely and inexpensively available that this disruption can drive innovation at many levels and different environments. Prosthetic fabrication is one such field where additive manufacturing is having considerable impact. This work specifically focuses on the fabrication of lower extremity prosthetic sockets. A socket is a critical component of the overall prosthetic system, as it is the interface between the more functional componentry in the prosthesis system and the human body. As such, it must be custom fabricated to ensure a proper fit and comfort. It must also support full body weight during single leg stance phase of walking and possibly even significantly higher loads depending on activity level. In addition, it is not at all unlikely that a socket may need to endure hundreds of thousands, if not several million cycles of loading over its normal life. These are substantial mechanical demands. While the basic concept of using novel additive manufacturing has been reported more than 2.5 decades ago. For example, the video you're seeing here on the left is about squirt shape, which was reported in the early 90s. The development and affordability of fused deposition model and 3D printing has really placed that somewhat esoteric fabrication in the hands of anyone who wishes to experiment with it. A quick Google search of 3D printed prosthetic socket yielded over 500,000 results. On the other hand of the spectrum, newer technologies like this shown on the figure on the right-hand side comes out of Hugh Herr's lab at MIT, where they've created this variable impedance socket, also using 3D printed technologies. But it seems that in between anybody who wants to do it and the high-tech approach, there seems to be quite a gap in the knowledge about how different material parameters and material choices contribute to a variety of functional parameters, strength, comfort, fit, regarding a prosthetic socket. Overall, for additive manufacturing of lower extremity prosthetic sockets, the impact of socket design methodology, as well as choices associated with these materials and 3D printing, the impact of these things on structural properties of the socket have not been scientifically, if at all, well described. So clarifying these relationships is essential to ensure a safe and appropriate socket can be delivered to patients, to develop consensus on best practices, and to quantify the benefits of this new approach. Mechanical work is frequently done by a prosthetist at the time of delivery after a socket is fabricated to ensure and to maximize the comfort and the fit. So we wanted to test this out on 3D printed samples, and so we had a quasi-convenient sample of 8 materials, and the table we're reporting the results on 4 of them, and the pictures are showing the results on 2 of them, just to contrast a good one and a bad one. But in short, these materials were heated, and then they were worked to be, curved a little bit, to be sanded, to be buffed, to be flared out a little bit. And you can see, for example, the gray material on the left really lost its integrity when the heat was applied and it was attempted to be flared, and that was PLA, versus the material on the right, which is polypropylene, which maintained a smooth surface and was able to be curved and to be sanded very well. On this slide, we report how different materials and different 3D print settings affect how long it took for our socket to be printed. And you'll see on the very far right column, those times vary significantly from 8 hours all the way up to about 17 hours. And so, again, this is the first time we're seeing this being reported in the context of a prosthetic socket. But the importance of this is this can really speed up delivery and burden to a patient for taking delivery of a socket. The last aspect of our work is proper mechanical testing, strength testing of these 3D printed sockets. It's our goal to do proof, cyclic, and ultimate failure testing in the Tinius-Olson machine. What you see here is one of our 3D printed sockets with the shiny metal objects or the custom jigs that we've developed to help us load the sockets in appropriate conditions. We're taking some inspiration from the ISO guidelines for prosthetic componentry to be able to kind of apply a similar sort of a standard to prosthetic sockets. So we're going to test them at a variety of angles to simulate the different angles that sockets would be in during normal walking. And we're also following some of the emerging literature that's coming that's doing a similar sort of mechanical testing on 3D printed sockets. So far, in some preliminary testing, we've seen some very good results, even with PLA, which is typically not considered a very strong material for this type of use. We've had some proof tests that have gone well over 500 pounds, so they're reassuring. To conclude, there is obviously a lot of additional work ahead with the additional testing, and there's a lot of sockets that need to be printed. We're also going to evaluate some additional materials, carbon fiber and things like that, as well as during the pandemic, we've had a chance to catch up on some other literature, some AM literature. We have found that there are other important parameters that are not as widely reported, things like raster angles and infill orientation and layer height that can also strongly affect the mechanical properties of a 3D printed object. So all of those are coming, and then we're also trying to work out a cyclic loading protocol that can be useful. Thank you very much.